clicker works as usual. Okay, thank you very much for this nice opportunity to come back here to ICTS. I was here for summer school, or I guess spring school 4 years ago, just before the pandemic, and it's really nice to come back here, and it's very inspiring to hear Rajesh's discussion. Can you hear me at the back? Okay. Yeah, I'll speak a little louder. Okay. So as I said, it's very inspiring to hear all the wide range of activities and groups that you have here at ICTS. So what I'm going to talk about today is about small x physics, and this is a kind of personal perspective on what's interesting and important to me in this field, and clearly this is one of the major topics of the electron-ion collider, which is the purpose of this talk. And so this is kind of the outline of my talk, and I'm going to emphasize that this physics is intrinsically non-perturbative, so you can kind of sort of run away from it, but you can't hide. And I'm going to show that, or just outline, how classical lumps dominate the physics and how they actually are a consequence of quantum coherence on very short time scales. And I will discuss some kind of more recent work that I've been doing and thinking about in terms of how to understand this physics in the language of quantum information science, in particular, the kind of Goldstone modes that result, when you break symmetries in this, at these very high energies, and how the Bekenstein bound can be thought of in this context. And this, as some people in the room know, has very strong connections to heavy ion collisions. Essentially, how do nuclei at very high energies collide and actually form the matter that eventually results in the quark-gluon plasma? And this physics is extremely fascinating. It involves many areas of physics, from turbulence to dynamical systems to also, you heard things like about the ADS-CFT bound for the viscosity. And this physics aspects of this physics is universal across energy scales. I'll briefly illustrate that at the very end. And I wanted to talk also about some recent work I've been doing on sort of connections between QCD and gravity at small x. There's some really exciting things which actually go back to some of the early days of holography. But since I'll be giving a talk tomorrow to the string seminar at 3 p.m., so if someone's interested, they can come and hear me. There's another topic that I'm kind of excited about, which is sort of a very interesting breaking of factorization in QCD at small x for polarized deep elastic scattering. There's a big role played. There's a strong connection between the so-called UA1 puzzle in QCD, which some people may remember, and the spin puzzle. And that was highlighted by Veneziano a long time ago, more than 30 years ago. And I've been studying its consequences at small x, and it leads to a kind of very interesting axion-like dynamics, where the spin that's carried by the polarized proton is quenched by topological Fallon transitions. So if one can actually measure certain observables at small x, so the electron-ion collider, you might perhaps see evidence with such remarkable transitions, which had potentially occurred in the very early universe. But I don't have time to talk about that in this relatively short talk, so if you're interested, you can look at some recent papers that have it Andrei Tarasov, and that's also work in preparation. So let's start. And so this is deep elastic scattering, this sort of cartoon that many of you are familiar with. And Bedangadas showed this kind of, what do you call it, phase diagram. So it's a landscape of the structure of protons and hadrons as probed at very high resolutions and high energies. So going to high energies is high parton densities and roughly scales as some power of 1 over x. So this is sort of the landscape where we understand very well corners of it. So at very high Q squareds and not necessarily very high energy. So the Bjorken limit of QCD, you have asymptotic freedom, so we can actually understand the partonic structure of what's inside. And that physics is weak coupling physics. It's perturbative. You can actually do systematic computations that we have heard about. We will be hearing about this week. It's a very powerful tool. And then as you go down in Q squared, the physics is very non-perturbative. So of course, that's a lot of hadronic physics. We have the lattice there, which is enormously powerful. You'll hear more about it. And then there's also chiral perturbation theory and so on. But there's, of course, this big elephant in the room sitting here, right there. And what I'm going to be talking about is kind of a peculiar regime here, which is where this is the so-called radial limit of QCD, where in the past, you only had low Q squareds in which to probe this. And this is the physics of total cross sections. And is defined by exchanges of sort of quasi-mystical objects like pomerons and regions, which we really don't understand fully in terms of the fundamental degrees of freedom or have appropriate effective field theories for. But the great advantage of high energy colliders is that we can also go up high in resolution now in the radial limit. And so one can sort of probe this very strong field regime of QCD also at weak coupling. And that's what I'm going to be talking about, is the kind of high density gluonic matter that results in this regime and its possible consequences. So trying to understand the physics here, going down this way and perhaps this way. And certainly this way, in trying to kind of map onto sort of standard decoupling EFTs and also just perturbative QCD. So there are clearly many open questions that can be understood in this landscape, and I'm going to focus on one small aspect of it. So weak partons are intrinsically non-perturbative. So what do I mean by that? So here's a picture of the hadron, low energies. You have your 3 valence quarks moving along at very high energies, well, very, very large momenta. So this way, when I say low energies, I mean sort of I have the physics is dominated by the valence degrees of freedom. And you can think about the gluons as sort of dressing these. So these could be your constituent quarks. And so these are sort of popping in and out of the vacuum around these valence partons. Now, as you boost the proton to, or hadron to very high energies, what's happening is these excitations get time dilated. So if you boost at very high energies and maintain very high resolutions, what you're going to see is a large amount of glue. And that's a very simple way to understand these kinds of plots that you see from Hera. This is from deep elastic scattering experiments of parton distributions as a function of X. These are the valence distributions. This is the glue and the C quarks, which kind of go along for the ride. And it's already at X's of 10 to the minus 2, you see that proton is completely dominated by glue. And so the way also to think about this in the sort of standard perturbed picture is that these partons are just Bremsstrahling of these valence gluons, and then so Bremsstrahlung leads to more Bremsstrahlung, and there's a kind of Markovian process that goes on, which is very rapidly, as we know from COVID. And so you can say, well, you know, aren't there powers of alpha S and that suppress this? And the point is that the suppression and the coupling for each additional emission is compensated by the large phase space. And very small x is very large, so there's logs that come in QCD. And these logs are order 1, so that doesn't suppress radiation at all. And so that leads to this potentially runaway growth that you seem to see here. And I'll come back to some of the consequences of that. But before I go on, I want to also mention that this small x physics is really what is at the heart of what happens in a heavy ion collision. So when you have nuclei collide at very high energies, you have the so-called Cronin effect, where the valence degrees of freedom just go off along the light cone. So they're very weakly coupled. They just pop off. And you form this mostly baryon-free region in the center. And that's really populated by the weak gluons that I mentioned. So much of what you see in these kind of iconic images from the star, as in the star collider, is you're seeing very large density of glue, which is very far of equilibrium in very short times and then thermalizes. And that's a very interesting process that I've been thinking about. There's obviously now an immediate connection to understanding the physics of the quark plasma broadly defined. Now, so let's sort of go back and say, okay, we have perturbative QCD as a powerful tool. How do we understand, this physics of, very rapid growth of parton distributions and weak partons in general? And so the way I think about these problems is really as always as a 2-to-n process to clarify my thinking. And I'm sort of thinking in Raju asymptotics. So this is very high energies, but so at fixed resolutions. And this is the sort of organization of such diagrams. So you have a plethora of diagrams, right, which contain lots of logs floating around, and one has to organize this, and that's why the Radici and Bjorken limits are very powerful. You can organize the logs systematically and then compute subleading corrections. And so so if you want to study multi-particle production, which is the physics of the quark-gluon plasma, for instance, then you want to think about this 2-to-n process. So you have some kind of ladder. And this was goes back to the really outstanding work of Lev Lipato, who sadly passed away about 5 years ago. And so you can sort of construct such a ladder of 2 gluons emitting n gluons in terms of the following building blocks. So one is the Lipato vertex, which at each, in sort of an organization in multi-Radici kinematics, which I don't have time to go into, it's an ordering in rapidity at fixed transverse momenta all along the ladder. At each rung of the ladder, you can think of that as a separate block where I'm summing over all Bremsstrahl and current possibilities. And you can use the Jacobi identity to write this as one sort of non-local vertex that's emitting, say, a gluon, and that's a Lipato vertex. And similarly, as you go down the ladder in the T-channel of this 2-to-n scattering, the bare gluons are replaced by so-called Radici gluons, where the 1/T propagators is multiplied by this factor here, it's alpha of T, times the difference in rapidities as you go between pairs of gluons down the ladder. And this alpha of T is nothing but the Radici trajectory in perturbative QCD, which one can compute. And you can compute in principle systematically order by order. So for example, this is the 2-loop Radici trajectory that was computed by Fadin, who's part of the BFKL equation here. Sorry? Oh, epsilon, this is the usual dimensional regularization, the pole. And so this is the logs. Okay, so you get infrared logs, which are this depend on some cutoff scale. And the whole magic of BFKL is this kind of bootstrapping where you have cancellations between sort of the real virtual contributions. So that's how the Pomeron emerges. And so, for example, the total cross-section for 2-to-2 scattering is imaginary part, twice imaginary part of the amplitude for 2-to-n in the forward limit. So for this function S at t equal to 0. And this goes as S to some lambda, where lambda is what is the sort of BFKL intercept. You can kind of compute this. And this is done to so-called leading logarithmic accuracy. So you sum powers to all orders in perturbation theory of alpha log x. And then in principle, you can go to next to leading log and next to leading log and so on. And this leading log object is the BFKL Pomeron. So the uncut object is a sort of what dominates the total cross-section is a color singlet combination of these gluons. And that's physics is described by a Hamiltonian, the BFKL Hamiltonian. So it's a renormalization group picture that emerges with a Hamiltonian. And this Hamiltonian has really remarkable, beautiful properties, holomorphic separability, can be generalized to an integrable XXX model. And there's also beautiful work in N equal to 4 SUSY for the supersymmetric BFKL Hamiltonian. And the state of the art is at next to leading logs, and there's work going beyond, and there's a very nice review, snowmass review by Vittorio Del Duca and Lance Dixon that I would highly recommend to you, to those interested in learning more. Yeah. Oh, sorry, it's 4 alphas NC over pi log of 2. It's 0.693. Yeah, I'm glad you asked. So if you just plug in alpha 0.2, say, so at leading logarithmic accuracy, you're still in fixed coupling. And so to see the running coupling effects, and that's why it's also conformal, the physics. But then if you go beyond, then running coupling effects come in, and that sort of modifies this picture substantially. In fact, if you put lambda equal to 0.5, this cross-section is much faster. Am I doing something wrong? Is that, okay. Yeah. Yes. Exactly. Precisely. And it's of course much higher than the intercept that you know from the soft Pomeron, and clearly if it were to continue, would strongly violate the Froissart bound, and so clearly it's something really off. Now the next to leading log BFKL construction, which took 20 years after the initial one to derive, so it's a very difficult computation. That sort of reduces the intercept somewhat, but it's still much higher than the soft Pomeron intercept. Yeah, so here's kind of, this is summarized, this is multi-radial kinematics, so 2 to n, so you have this momentum transfer in the T channel, and then is the KTs of the gluons that are emitted are roughly the same, and there's an ordering in X as you go down. So now you say, okay, you did this perturbative construction, what's the issue? That's all good, but so here's the crux of my statement why the physics is intrinsically non-perturbative, is that even if you start with this construction at arbitrarily high transverse momenta, which would presumably control the running of the coupling, so no matter how high a K-perp that you start with, if you go to sufficiently high rapidities, a small of x, this initial distribution, which say you chose some initial distribution, which is say peaked like a Gaussian, say, of the distribution of gluons, the single inclusive distribution of gluons, say, the amplitude in the forward limit, then that would get, as you boost it, it would sort of go into the infrared. So it's actually infrared sick. And this was very nicely there's a very nice paper by Al Mueller who sort of addressed this problem. And this is one of the things that also influenced me quite a bit. And here's a statement. He says, so any fixed large Q squared, so you can think of this as a proxy for Q squared, there's always an X such that below X now the OPE breaks down. So the operator power expansion breaks down the radial limit. And so you are unavoidably sensitive to significant non-perturbative corrections, which are higher twist. And there's a sort of diffusion that takes place. The BFK equation is a diffusion equation, so it leads to diffusion in rapidity, and so that diffusion sort of goes off. And the next to leading log BFK doesn't cure this problem. So you can do perturbative QCD with all the best intentions in the world, and you will be sensitive to this physics. So what's going on? And so that's the physics of high parton densities. So what's happening is that if you keep phase space fixed and then you increase the rapidity, you're populating your hadron or some region with more and more gluons. And at some point, they start to feed each other. Unlike the Bjorkian limit, where things get smaller and smaller, so you're always in this sort of dilute picture. But if you are at small x, at fixed resolution, then you're going to be sensitive to many body sort of so-called recombination effects, where two softer, slower gluons can combine to form a faster gluon, so that's recombination. And then there's also screening contributions. So often when people talk about small x physics, they talk about it as a competition between Bremsstrahlung and recombination, and that's actually wrong, because this cut, actually, so the cross-section is a sum of various possible unitarity cuts. This cut actually leads to a positive sign, so it leads to a growth in the cross-section, but it's actually these screening corrections that flip the sign and actually give you something that depletes the cross-section, and that grows as a square of the gluon distribution over the resolution. So this is sort of the phase space density. So if you have fixed Q squared and sufficiently small x, this becomes a number of order 1. And so you get sort of death by a million cuts. You get more and more sort of higher twist contributions which are contributing. And very amusingly, there's a beautiful paper by Weinberg. This is before QCD, okay? Before, there was Yang-Mills theory, of course, but this is in the 60s. And this is his famous soft photon and graviton paper, and he talks about, this beautiful theorems that he invented there. It's really a really fascinating modern paper. And in that paper, he talks about Yang-Mills theory, and he says, how fortunate that we are that the world is not actually, Yang-Mills doesn't describe the strong interactions, because if it were, then, he immediately saw that the kind of complicated divergences which simplify in gravity and in QED would become, because color charges could sort of interact with each other, and you get all these, and that would be a Herculean task. So it's really a good thing that Yang-Mills' work. So of course we know he was wrong, but it was incredible how prescient he was. And there's, of course, a much later quote by Wilczek where he sort of talks about, again, this recombinations, you can think of it as shorthand, but really one has to understand that there's very complicated screening that's going on that actually is what resulting in the depletion of parton densities. So what happens? So there's emergent physics. So you populate a region with more and more glue, and at some point, what happens is that you get all twist corrections, very equally important, and that happens when the phase space density, sort of defined simply in this way, becomes of order 1 over the coupling. And so if you try to go beyond, there's a kind of Nielsen-Olesen kind of instability that will sort of cause this, those configurations are highly suppressed in the cross-section. And so the physics actually becomes classical. And so where it becomes classical defines an emergent scale, okay, and that scale is called the saturation scale. So there's a self-consistent kind of picture here. And so if you're at sufficiently high energies, that scale is much larger than lambda QCD. So there's an emergent weak coupling scale, which is highly non-perturbative because, all twists are important and these are of order 1. And so this is kind of the essence of this statement by Al, that, for fixed Q squared, there's always an X where things kind of break down. And so one can also think of it sort of in this language where you have you think of the S channel. So there's also an S channel picture of this scattering. Earlier I talked about a T channel picture, and there was sort of a beautiful sort of dipole picture of BFKL that Al Mueller came up with, which also describes this process. So you can sort of understand this now, this density in terms of, say, a virtual photon that scatters off a dense object, and then that photon goes into a quark-antiquark pair, which then forms more and more dipoles. So that's the S-channel analog of the 2 to N that I was talking about. And then at some point, it becomes so dense that the scattering of this object saturates the unitarity, even though, perturbative unitarity, even though it's much smaller than lambda QCD scales. So essentially, this dipole object is seeing blobs of color on very short distances, and that's kind of illustrating this cartoon where on the y-axis are the boost of the dipole, say, as opposed to its resolution, so the inverse size of it. So any given resolution, if you go to sufficiently high energy, so if you boost that object relative to at very high energies, it saturates unitarity. And you can, so therefore understand equivalently Al's statement as a saturation of perturbative unitarity, and it also occurs when the occupancies of order 1 over alpha. And there's a very simple model when the Hera data first came out called the Golek-Biernat-Wustau model, which really captures the essence of this. So if you think about, again, this S-channel picture, you have the cross-section of a quark-antiquark pair, which then scatters with hadron, and it has some size and some energy. And you can sort of write that as some non-perturbative cross-section times such a survival probability. And so that's your saturation scale, and it's an emergent scale, like I mentioned, and that grows with X. So in other words, and that's, as I was saying, is for any fixed resolution, there's an X. So that's the QS of X line that you have here, and its exponent is given by the Biot-Friedel eigenvalue that the 4 alpha SNC over pi log 2. Now, this S-channel picture is very powerful, because it also allows you to think about this problem more broadly. So instead of hadrons, now if you have nuclei, so nuclei, of course, this is not nuclear physics in the traditional sense. Here, nuclei are just bricks of large amounts of color charges. And the reason is because at small x, the coherence length of the probe is much longer than the Lorentz contracted width of the nucleus. So essentially, the weak glue sees, okay, large amounts of glue from all the different nucleons along its trajectory. Okay? So on average, it might see 0 color, but it's going to see a very low, so it's a sort of random walk. And so this saturation scale that it sees gets a huge oomph by the sort of root mean square distribution of color charge. So one can actually work that out mathematically. And you see that this goes as 8 to the 1/3. So that's a huge oomph. So if you were to do deep elastic scattering of nuclei at very high energies, the dynamics is then controlled by a scale which is much larger than the QCD scale. And so there's some very interesting physics associated with that. So this explains very simply phenomena that you hear in sort of talks of nuclear physics and about things like color transparency. That's just saying that when the size of the dipole is much smaller than the inverse QS squared, so when R squared times QS squared is much less than 1, then the scaling of the cross section just goes as the nuclear size. Okay, so for any fixed impact parameter, it goes as 8 to the 1/3, and then there's the integration over impact parameter that gives you the other 2/3, so it scales as nuclear size. And the other limit where the survival probability of a small dipole goes to 0, right? So it doesn't survive. So this is the S matrix. The S matrix goes to 0. That's when this is much larger than 1. And that tells you the cross-section scales to the surface area of the nucleus. So that's the black disk limit. And this explains this phenomenon of shadowing kind of in a kind of microscopic sense that this is perturbative QCD, the Bjorken limit, and this is the physics of the radial limit. And this is a very strong interactions, right? So if you're at very high energies, an arbitrarily small dipole will have an S matrix that goes to 0 at sufficiently high energy. So that's the essence of the physics there. Now, can we kind of understand this in a systematic EFT? So when you ask, is there an EFT, the first thing you say, is there a Born-Oppenheimer kind of separation between fast and slow modes? And indeed, on the light front, you do. So again, you think in this S-channel picture, you have a dipole scattering the hadron. There's all this glue here. And so the dipole interacts with the slowest gluons compared to the fast ones that go with the hadron. And so there's separation time scales. Okay, so the fast gluons are on the light cone. They're going at the speed of light, so they're static modes. And then the small x gluons are fully dynamical, so they interact. So that's where the whole dynamics of QCD comes in. So you have a separation of scales. So you have static sources which are living in the light front, and there's a large number of them as seen by the dipole because they're coherent in X. So there's quantum coherence of these. And so there's a large number of color sources, and they live in some higher dimensional representation. And so you can think of them as classical sources. So you can write down a path integral for those with some weight. And so this, you can write a generating functional for this. You can work in some particular gauge. And there's a scale that separates, in between fast and slow modes, the stuff that goes into the color distributions of large X modes and those that interact with the dipole. And so that's the scale here that separates the distribution of these modes. So these are stochastic, this is stochastic distribution. It's a highly non-trivial one because it contains information about all endpoint correlations in QCD. So it's not a one-body distribution. And this leads to a kind of Wilsonian picture that I'll talk about. But before I go there, you can actually do an explicit construction for a very large nucleus of this EFT. And there's this very beautiful group theory that emerges where you can sort of understand these objects, for very high representations, just given by the Casimirs of SU3. So you have the quadratic and the cubic Casimir here, and they are what very simply correspond to what we have always thought of as Pomeron and Hadron configurations. So all this language of Pomerons and Hadrons and so on gets kind of translated just into sort of the dance of these partons in the group space of SU3. So these are the stochastic distributions. Yeah. So it's like, think of throwing dice, and I have so large numbers of 3s and large numbers of 8s, and the most likely representation is the one with the highest rank. And so you can study the distribution of representations. And this is the corresponding distribution of representation. So the most likely representation becomes a classical one. if you have a large number of sources, and that's what a large nucleus is a large number of sources, and it's coherent. And so we know the weight functional, it's essentially a Gaussian with a cubic correction, so you can compute all n-body correlators. And because you have large A, you have a large initial condition, which gives you a sort of weak coupling scale, so you can actually compute all n-body correlations in such an EFT. Okay? It's a 2D EFT, so the dynamics is completely in the transverse plane of what's going on here. So if you ask, what is the classical solution this corresponds to this path integral, that's this kind of shock wave solution. So all these gluons that's seen by the dipole probe, they sit on a 2D transverse sheet, which is localized at x minus equal to 0. So it's Lorentz contracted. And the solution, so you can solve the Yang-Mills equation. The solution is remarkable. So this is in Minkowski, so it's Lorentzian, right? And on one side you have a pure gauge, and the other side you have another pure gauge. So they're separated by two large gauge transformations. The transverse dynamics on the sheet can be mapped to a celestial sphere at null infinity. So this is a kind of picture in terms of retarded coordinates. So U is like retarded time, and R is of course the radial coordinate, and then you have these holomorphic coordinates, Z and Z bar, right, which are just complex X perp and Y perp. And you can do the following map between X plus and A minus and X perp to these celestial. So you can map the transverse dynamics to a sphere, okay, to the surface of a sphere, but simply. And so if you take infinite boosts that's given by this lambda, essentially R goes to infinity, X plus goes to infinity. So you're taking the sheet and sort of transporting it to infinity. And the reason you can do it is because the dynamics is static in time. And that also causes shrinkage to X minus equal to 0. So essentially the entire dynamics can be mapped to this dance of weak partons on the surface of the celestial sphere at null infinity. And so this is where kind of the language of symmetries comes into high energy scattering, where you can think about these weak gluons that live on the surface. So they have very high occupancy. It's 1 over alpha. And they can be understood as Goldstone modes of a broken Poincare symmetry in the global subgroup large gauge transformations. And they can be understood to satisfy a current algebra on the celestial sphere. Now, why are these thought of Goldstone modes? And this is kind of very strongly inspired by this work by Andy Strominger, where he sort of again, try to understand amplitudes in the language of symmetries and establish sort of connection with so-called well-known soft theorems in gauge theories between asymptotic symmetries. So his initial focus was on gravity. So these were asymptotic symmetries of gravity and a so-called memory effect, okay? And the memory effect is what kind of interested me because I realized that that's nothing but the kick that a dipole goes from traversing one pure gauge to the other. And so that's, in this case, that's given by this saturation scale QS. And so there's kind of a very nice map between these different languages and in such that one can think about these weak gluons as Goldstone modes. Now this turns out, I've since realized to be not quite right, but the reason it's not quite right is very interesting, but I'll not have time to go into this. And so if you think about now computing in this framework of very strong fields, what you're actually doing is solving Katkowski's rules, which is the usual sort of rules for computing Feynman diagrams and perturbation theory. But you're doing it in the presence of strong fields. And there, so Katkowski's rules in strong fields are very interesting because they're not trivial compared to usual Feynman diagrams, because you have closed diagrams which are given by these blobs. So these are all closed loops. These are just tree-level closed loops. So you can have cuts where you can just cut a closed loop like this, like you can just have a one-particle cut, which you can't have in ordinary perturbation theory. You can't just cut one line. You'd violate energy momentum conservation. But if you think about these sources as sinks, then, yes, you can think of them sinks or sources, then you can have such diagrams. And then essentially you sort of introduce sources, positive and negative sources and coupling, so you can construct everything on sort of the Schwinger-Keldysh contour. where all the time-ordered propagators sit. So these are Feynman and anti-Feynman propagators, which sit on the two sides of the contour, and your so-called Whiteman functions, which connect the two things. And those correspond to these cut propagators here. And so this is well known actually in quantum field theory. So Schwinger pair production, strong field QED is a very sort of well-known example of this. But my claim is this also applies more generally and in particular to the Ray-J regime in QCD. And so in fact, if you know a lot of Russian physicists from the old school, they would sort of, when I was younger, I'd go around and sort of ask them about this, and they say AGK, 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 and I never knew what that meant. And that was, you know, Abramovsky, Gribov, Concelli cutting rules. And that I've learned, and this is some work I did with François Gélis about 15 years ago, is that we could sort of reinterpret all of this just in terms of Katkowski's rule. So it's a very general consequence of unitarity in strong fields. And it's completely independent of this language of Pomerans and Regions in which these gentlemen sort of did their construction in. So you can really think of it as a shorthand for thinking about sort of unitarity in the present strong field. So maybe, you know, what one needs is a paradigm shift. So this construction that we've sort of been chasing after, what are Pomerans, what are Orderons, are nothing but the simplest constructions that enable one to enforce strong field unitarity and sort of, yeah, I'm kind of running out of time, I know. So anyway, what I wanted to say is that there's an EFT that describes this physics. And there's renormalization group equations that describe the evolution of source and fields with change of the rapidity scale. So there's some references here. And so let's take a very particular example. So just think of this S-channel picture of dipole scattering with a strong shock wave field. And now imagine that this dipole emits a gluon, which also scatters through the shock wave field. So this is described in terms of Wilson line correlators. And you can write down the simplest renormalization group equation, this EFT, and sometimes called the Bilitsky-Jimbo renormalization group equations. And so this is just the one for the dipole, so quark-antiquark pair that interacts with the shock wave. And that has this nonlinear kind of equation where on the right-hand side, the correlator of these dipole Wilson lines where the quark or antiquark scatters the shock wave, so that's V of X or V dagger of Y, that now gets this additional scattering of the gluon, so that's kind of these Wilson lines here. Okay, and so this doesn't have a closed form expression in general because you have 2-point correlators related to 4-point correlators. And in principle, you have an infinite hierarchy. However, for large A and large NC, you get a nonlinear renormalization group equation. And these describe so-called fan multi-Pomeron type diagrams, which are actually which actually give you a very non-trivial fixed point. Okay, and so the solution to the RG equations is that you get a non-trivial fixed point that saturates cross-sections fixed impact parameter, and they actually define this close packing scale. And this is what cures the infrared diffusion that you see in the BFKL equation. And so it's a non-trivial fixed point, and there's a trivial fixed point, and that just comes from expanding these Wilson line correlators to the lowest order in the sources, and that just gives you the BFKL equation. So this T-channel construction, which is very complicated, is very simply reproduced in this S-channel picture. And now one can sort of look at more complicated final states involving, you know, multiple gluons that are measured that scatter of this. And so there's a kind of Langevin-like dance of weak partons in the space of color configurations. So you can look at dipole, quadrupoles, and so on. But there's an elephant in the room, and that is, of course, confinement, because all of this construction implicitly assumes fixed small impact parameters. If you sort of go to larger impact parameters, this whole sort of construction breaks down. So even if you start with a very sort of initial condition that's very sharp in impact parameter, with one step in evolution, you start again seeing, so this isn't rapidity, you see the emergence of a Coulomb tail. And this Coulomb tail, of course, you know, just violates, that's just a QED Coulomb tail, so there's no mass gap, obviously. And this is the missing physics of quark and gluon confinement. So an outstanding question, I think, for this field to resolve, and you know, I've spent over 20 years thinking about this, is, you know, how do you kind of understand the structure of hadron in this kind of picture? So there's maybe some black disk core, there's a parton regime, and then maybe there's a pion cloud. And how does this all kind of work consistently with everything we know? And that's kind of an outstanding problem. Now at the EIC, as you heard in several talks, you'll have really remarkable ways to probe this, the space-time structure. And so these GPDs that people talk about, generalized parton distributions, are as relevant for very small x physics as they are for anything else. And they're going to help us kind of, from experiment, isolate these different regimes. And good models can help us kind of gain further insight and complement kind of this RG picture that I was talking about. And so there's a huge amount of work at small x, and I tried at some point to kind of put in the key works here. So there's the small x evolution, there was leading log, and then there's next leading log. And you see with each advance, it takes another 20 years or so. There's resummations that one has to worry about. There's impact factors for different final states at next leading order. There's a lot of work done on jets and so on. And so it's a very active field. In 2023, there were 30 plus papers, so I couldn't just put them all here. I just want to mention one piece of work that I've been involved in, and this is with these kind of brilliant collaborators. And so that's looking at back-to-back dijets. So if you think about a DIS process, where dipole comes in and forms a jet that's back-to-back. And so that's characterized by its overall energy of the jet, the PT, and its momentum imbalance. Okay? And so if you look at the momentum imbalance, that's actually sensitive to all these saturation effects, because that's like coherent multiple scattering. So that imbalance, it's like this color memory effect that I was talking about, is going to be sensitive to that physics. And so it's very important to calculate this with high precision. And so this is the cross-section next to leading order. So it's a full cross-sec, complete NLO computation. And there's a very nice factorization one sees for both transversely and longitudinally polarized photons, virtual photons. And so this cross-section contains the Weizsäcker-Williams distribution. So this is the QCD analog of the QED Weizsäcker-Williams distribution. It's a highly nonlinear object that satisfies an RG equation. And that's multiplied by these Sudakov factors, which sum both double and single logs of the jet momentum and its imbalance. And we have computed all the finite pieces as well. So these are these Fs, where they're hiding here, going blind. There are these F1s and F2s, and they're pure alpha S contributions which are computed. And so here's kind of a plot of the ratio in an EA collision to EP as a function of the momentum imbalance. Unfortunately, at the EIC, the kinematics is highly constrained for jets. And Elka, I'm sure, is shaking her head in disbelief that I'm using these numbers. But okay, we try to go sort of the edge of what seems somewhat reasonable. It might be easier to measure dihadrons and jets, but we thought, okay, we should at least do the full calculate. I mean, it's much cleaner to do jets, there's no question. And we chose relatively modest numbers, but these may be challenging. And you see that, so the leading order thing is, this peak is the so-called famous Cronin peak that just describes multiple scattering. You shift momenta from low momentum imbalances to large ones just because of multiple scattering. But then when you go next to leading order, the Sudakov logs, which are the logs that suppress the edge of phase space, they already give you a huge, sort of suppression. And then when you include all this nonlinear, the shadowing due to these nonlinear evolution, that leads to a further suppression. And so these correspond to the various uncertainties in the computation that I won't go into. So there's a window to really see both of these effects, the interplay of both of these, if you study different nuclei and so on. So for example, if you look at the same thing at a fixed imbalance as a function of 8 to the 1/3, so at the EIC, you can go all the way up to gold and uranium. And you see a systematic suppression. So this is an NLO computation. So there is definitely a window for discovery. But really what one needs is to compute a whole suite of such NLO, and maybe by the time of the IC NNLO in this framework. By the way, some of it already includes NLO, and so the evolution equations are next to leading log accuracy. Okay, so but the whole the impact factors or the coefficient functions are only NLO. So we can do global analysis to extract, and so we also need to look at PA collisions at LHC. I think it's vitally important. There are new detectors, for example, focal that's being designed to look very forward that can go to much smaller X than the EIC with added sort of uncertainties due to the nature of the proton and the nucleus that's colliding. So you win in X reach, but you lose in the cleanness of the interpretation. But I think it's very important to do such global analyses. So I want to go into this next thing, but I'm out of time. And Olga is a good friend. She's been very kind, so thank you very much. But hopefully I'll get a chance to talk to you separately about this.
Thank you very much, Raju. So let's still try, maybe grab a couple of questions. Okay. If there is quick ones, please.
So you mentioned about this diffusive gluon sort of gas.
Right.
And you also mentioned about the fact that there can be collisions with higher representations coming in. And there's also mention about coherent state of all this stuff. So this must be related to some classical solution that also there was mention of what effective action. Right. This is the classical solution. Which effective action?
Right. So that's this color glass picture that I was talking about, and there's an effective action where you separate the large sources which are static from the small x dynamical modes, and there's an RG that describes that, and it has features which are like that of a glass because even though it's completely bosonic, there's a real separation of time scales. So there's very slowly changing dynamics, and then there's very fast dynamics. And so that's why you can sort of separate the two dynamics, with one being a stochastic weight. And the RG equations are really the RG equations for this weight. And that gives a whole hierarchy. It's an endpoint hierarchy, like the BBGKY hierarchy of endpoint correlators. But the great advantage is that it's in this two-dimensional transverse space. So one can actually solve that hierarchy to some, at least at leading log accuracy. And there's some nice Langevin type picture of that.
What about gauge invariance in all this stuff that you do?
Right, so the weight functionals are gauge invariant by construction. Okay. And of course we work in a particular gauge. We're doing perturbation theory. Actually I would say weak-coupling, it's a weak-coupling framework. However, if you engage in invariant observables, so if you're doing things carefully, you can extract gauge invariant information.
Thank you. Yes, please. Let's do one more.
Yeah. What would be some of the experimental observables for color, gluon color glass condensates?
Yeah, so one of them was the one I showed in the last slide. And I think you look at back-to-back jets or dihadrons, and you can study this imbalance systematically. And that's what these analog computations are designed to really compare with. And there's that systematics that I showed of how things behave as a function of nuclear size, or with QT, and you can look at other sort of other kinematic variables. But there's also a whole suite of things. You can look at diffractive. So diffractive final states are extremely sensitive to such effects because diffraction is proportional to square of the gluon distribution from the very start. And so coherent diffraction. So all these rapidly growing effects due to small x are heightened. So it's also, so in that sense, it's day one physics of the electron-ion collider. That there are predictions for what you would see, which are very large cross sections as a function of nuclear size, that should tell you already whether there's sort of such physics that's going on.
Expect the phase to switch on rapidly or swiftly, or it's gradually?
I think it's gradual. I mean, so it's not. So you can ask if there's some kind of quantum phase transition that goes, but I think it's more like a percolation transition in that sense. But I think, so the other question is, I mean, there may be something really interesting along those lines, which is worthy of thinking about more. So in fact, the model for directed percolation was Reggian field theory, actually. So there's some kind of, but the question is whether the experiments really have the resolution to really see some changes along these lines. And there's no evidence so far that that's the case, but it's still worthy of thinking about whether in certain but whether you can look at, say, higher point correlations and so on and see some non-trivial critical behavior.
Let's thank Raju for
Thank
nice
you very much.
talk.
Sorry for bringing.
And I have a question to ask you about this signature tomorrow
Okay.
in my talk. And we have a